by the time of our next class, I'm going to ask you, I cannot require you to continue to wear masks in class, but I'm going to ask you in deference to my age to continue doing so. Questions on anything? Okay, today we're going to focus particularly on the idea of scale space. So thinking of an image not only as a function of position, but also as a function of scale. So think of a 2D image that has above it the image information at all sorts of different scales. Right? And for the time being, we will talk about act as if that's continuous in both position and scale. But we'll have to get to the question of how we sampled both in position and in scale. But from that continuous point of view, if you have a 2D image, it will then be understood in scale space as being a 3D image. 2 dimensions of space and 1 dimension of scale. Right? And likewise, for a 3D image, it'll be now understood in scale space to be 4D, right? 3 dimensions of space and 1 of scale. But before we talk about all the matters of scale and scale space and so on, I need to cover 2 more of the ways of representing an image that has the opportunity for a choice of scale. And we've talked about 2 of them, Gaussian derivatives and splines. And I need to talk about the other 2, the Gabor wavelets and the orthogonal wavelets. By the way, the Gaussian derivatives themselves are often called wavelets also, but you'll find the people who have the orthogonal wavelets as a religion tend to not use the word orthogonal. They just say wavelets. And when those people say wavelets, or a lot of people say wavelets, they mean the orthogonal wavelets, even though other people use wavelet more generally for any of these other than the splines, although you're going to later see a relationship between the splines and the wavelets, the orthogonal wavelets. So for the Gabor functions, we're talking about a aperture which is a Gaussian and sinusoids within that envelope of the plus or minus Gaussian. And the notion, though, is although you could, in principle, for a given aperture, use an arbitrary wavelength, you don't want to do that. The idea is that if you want small level of detail information, then you should use a small aperture. And if you want large level of detail information, you should use a large aperture. And so typically, at any given aperture size, you want wavelength that only has a 2 or 3 different wavelengths within that. Typically, the wavelengths will be some multiple of sigma. Okay, so you might have one with wavelength sigma and one with wavelength sigma over 2, and maybe another one sigma over 3. But that's all. And then you want higher frequencies, that's to say smaller levels of detail, you can correspondingly cut down the sigma and have the few wavelengths at that. Okay? So the major proponent, lots and lots of really good results in for the Gabor functions is Wechsler, who wrote a book called Computational Vision, all about wavelet stuff. If you're interested, nothing required in this course for that reading. The particular use of the Gabor wavelets in the image computation literature is for dealing with texture. So if you're trying to talk about well, let me see if I can find the slide that I had here. Okay, so if you're trying to deal with these little squares, not square by square, but as a texture, and you want to be sensitive to the texture or measure properties of the texture, that's where a major fraction of the use of the Gabor wavelets are. And because texture has, sort of size aspects, these little squares in this example, but also directional aspects, you may have the texture going, diagonally or some other angle, and it may vary across the image, so you may sort of swing around as you go. And texture it can be a very important feature, and we're not going to cover it essentially in this course beyond what I'm saying now. It's important to have a sensor that is equally okay in any direction. Okay, so the texture doesn't have to be horizontal or vertical. You may want it to be able to sense it at other angles equally well. And as a result, you want a basis which is isotropic, is not biased to direction. And so now, if you really want to be mathematical about it, you would have I of x, sigma, and angle as your space, right? So you have lots of different angles that you can sense at, and so on. But in any case, because sinusoids are, but even though applied separably, even though they're applied in x, computed in x, and then on y in the result, they are nevertheless isotropic. They're equally sensitive to other angles. And so are the Gaussians. And so the combination of Gaussian and sinusoid that forms these basis images there are these Gabor wavelets are also isotropic and thus well suited for dealing with texture. Okay. Any questions about the Gabor wavelets? I'm not going to emphasize them beyond what I've said today, but they are an important option. The next and final of the 4 multiscale analysis methods are these orthogonal wavelets. The orthogonal wavelets have this interesting property that a single basis, global basis image forms, from it you can compute all of the other basis images, right? basically you get the original basis image, and then you get it scrunched by a half, or scrunched by a quarter, or scrunched by an eighth, and scrunched by a 16th, and all of those are used in this way where the sampling also depends on the scrunch. And so the black region here, the whole image, would use the base wavelet, and then scrunched by 2 would be for this square, and this square, and this square, and this square. And scrunched by 4 would use the red subsquares, and so on. And notice the particular positions that we're talking about are the centers, if you will. Well, the squares are centered at a quarter of the image, an eighth of the image, at a quarter, a half, 1, or eighth, or 16th, or so on, specifically. And so if you take an image of my hand and you center it and you get some sort of values for it, you get an interesting representation. But if I shift it just a little, it'll cross these boundaries between the sampling squares, if you will. And you don't get translation invariance. You get perfectly good representation in the sense that you can build from the coefficients of the basis images a good overall image. But if you want to use the coefficients to measure something you care about that has to do with the objects in the images, where there's a bar or something like that, it's not very good, because the barness information you get from a bar that's at one position is quite rather different from the barness information that you would get at another translation. But the big deal is that all of these guys are orthogonal, and as a result, you can use dot products to compute coefficients, which is fast. Not as fast as an FFT, but nevertheless fast, especially since the dot products for the smaller scales are only over small squares. They're not over the whole image, right? Okay, so both like splines, wavelets are applied separably, the orthogonal wavelets. And this is not isotropic. So the Gaussian derivatives, although all 4 of them are actually computed separately, meaning you do x first and then y, or y first and then x, or in 3 dimensions, whichever order you want to do, z and then x and then y, or for that matter, you can pick a u direction and a perpendicular to u direction and a perpendicular to u and that second direction, and so on as the directions. Whichever you do, you won't get different overall effects from the measurements you make. You won't have a bias to rotation. But splines and orthogonal wavelets, also applied separately, computed separately, but are not unbiased. The directions that you apply them in get better sensitivity to changes in those directions than in, say, diagonal directions. Okay? And the result of that is that what you're really doing is one-dimensional x for some position. For example, the center position, the wavelet goes in x from here, and you'll also get a wavelet with the next level wavelet. This black centered here, and then we'll do the next level wavelet from this range to that range, and the next level wavelet and so on. And the question is, at what scale in y do you choose when you're going to have smaller scales in x, right? So you could do, but normally don't do, full scale in y for smaller scale in x. Okay, but normally you wouldn't do that. And so in order to do that, you need to have done the scale, the x scaling, x for this row, and for this row, and for this row, and for this row. You get the idea. Yeah?
Why wouldn't you might want to scale the y very large? It seems probably like more computationally efficient.
Well, you could, but it...
In like a particular case where you're only...
okay, so you could, but then you would only want to do that if you knew that you had features that were sort of long in y and shorter in x, right? Otherwise, I mean, in other words, if you wanted a bias, you could put in that bias. But normally, if you want to not be biased by scale, then you wouldn't do that.
Is that considered a benefit of using orthogonal wavelets, that you can change the bias?
Well, small benefit maybe. Okay, but anyway, the point is that you end up doing x and then y, or y and then x. Okay, and the one final thing I want to say is what really goes on is not a single base object that is whose job it is to apply, for example, to the whole image. Because in the scale space idea, what you would like is the part that has to do with the whole image is only about something that has level of detail related to that large scale. And you would like not to be reflecting information at smaller scale in this large scale information. And to do that, you need a different wavelet that in essence is the difference between a wavelet, this kind of a wavelet, this kind of a wavelet at one scale and one at the next scale. The next scale down is a half. And by the way, notice the specific decimation level of a half that you're restricted to in order to get the orthogonality. Okay, so the upshot is all of what I said is so, except the actual wavelet that you use is already designed to capture the only information at this scale and not have a strong response at other scales. It's already sort of focused on this particular scale in question. Okay, so I've now, over here, in these 4 places, indicated relative strengths and weaknesses of the 4 different ways we have we've covered for doing multi-scale with locality analysis. So, starting with the Gaussian derivatives, they are isotropic. That's nice. Which means, but they're not biased in rotation. They're also not biased in translation. Or scale. Isotropic and other invariances, namely scale and translation. They are not orthogonal, which means you can't use dot product to compute coefficients. But if you want coefficients all over the image anyway, you might as well go over and compute them in the frequency domain, where the FFT buys you a lot. So you have another means of getting speed, namely coefficient calculation via the FFT. So it's a bit of a negative, because the FFT gives you coefficients globally, and if you only want them for a particular subregion, you're doing a whole lot of extra calculation. You can compute this at whatever sigma you want. And we're going to see how we would use them for edgeness or barness. Since edgeness and barness are so important for finding objects in images, you would like to be able to do that. And we've already seen more or less by your homework how to do that. Edgeness is going to be via first derivatives and barness via second derivatives at optimal orientations, if you will, where you try to optimize over not just scale and position, but also over orientation. The Gaussian wavelets are also isotropic, and they're also non-orthogonal. But because you can understand the behavior of the sinusoid in sort of separated from the effect of the Gaussian, there are ways in which you can employ the FFT in computing its coefficients as well. So that, again, not dot product directly with the basis images, because they're not orthogonal, but possible use of FFT, and as I said, very good for texture, commonly used for texture. The splines are great because you don't have to compute the coefficients after having the basis images. The coefficients are the control values, right? and you compute those from, well, whatever source of information you have. For example, averages over the aperture. And so that saves you the time for having to go separately compute coefficients. They are a basis that any individual basis element is approximate, but that's okay, because at large scale you're not after precise values of the image, for example, because you use the other scales, the other levels of detail, smaller patches with correspondingly smaller apertures, to make things even more precise and successively as you go down by scale. The basis images for splines are what? They're polynomials, right? And they're known polynomials. You have the formulas for them. It's easy. Polynomials are really nice for computers, right? Because, the computer's basic operations are addition, subtraction, multiplication, and division. And that's what you need, just actually, literally, addition, subtraction, and multiplication for computing polynomials. Whereas things like computing sinusoids is more time consuming to compute on a computer. So realize when you have an explicit function like polynomial or like specific sinusoids, you can evaluate those guys not just, let's say, at the pixel centers or at the aperture centers if you're in a locality, but at any place. It's just if you have a polynomial of the form a t cubed plus bt squared plus ct plus d, put in any t you want, not just the specific ones that we have as pixels, and you can go ahead and evaluate that, right? And that's going to be pretty important to us later when we want to start talking about transformations on images, where the image, for example, we want to rotate an image to make it fit some other image or some other template we have for the image. And now the pixel centers that were at the original image are no longer the pixel centers that we want to evaluate the image at. Okay. What splines are biased orientationally? The orthogonal wavelets, because of the orthogonality, makes the coefficient calculations fast by a dot product, but you're stuck with this binary decimation in particular. A half, a quarter, an eighth, a 16th. You can't do a third. Right? And you can't do 1 over root 2, and we're going to see in a moment that 1 over root 2 is an interesting possibility. And that means that you have not only orientational variance, but you have translational variance as well, not invariance to small translational shifts. Yes?
So, I sort of see you can't do a third. Could you do a fourth? Or would it just not be as good?
Could you do what?
Instead of your binary decimation, could you do sort of decimation
No, not with it does not well, not unless you rebuild the basis images to do residues between quarters rather than residues between a half. Oh, even it's worse than that because now you would also need to modify the level of detail to include, when you're doing a quarter, the scales that are sort of between a little bit less than 1 and a little bit less than a quarter, right? Because you've ignored the 1.5.
Right.
To make a long story short, you could probably build that. You probably don't want to do it. Yeah.
You mentioned, did you say that you can or cannot do 1 over root 2?
You cannot do
Okay.
1 over root
That was
2.
true.
Only powers of a half. Integer powers of a half. Okay. I'm done talking about the individual pieces and their comparison, although at the end I have a table you will see that says some of these things again. Great. I've already said this, but I want to emphasize it. People confuse separability and isotropy. Isotropy means you're not biased by orientation. You can still compute things separably, but the result is not biased by orientation. Meaning if you compute them in x and y, and now you want to find directional derivatives, for example, in some other direction, it's just the same as if you had done it directly in that direction. Right? Or alternatively, you can do it in an image, at 2 other orthogonal directions and compute what happens in x and y. And again, there's no extra bias by dot product on your derivatives if you're doing Gaussian derivatives. Dot product of a direction vector, I'm talking about. Separably is a matter of computation decision, whether it's either okay in some of the cases or required, but in others of the cases, that you compute it first in one direction and then in the other. That gives you computational efficiency to do it that way than to try to do it fully in 2D or fully in 3D. Right? But for splines and for the orthogonal wavelets, that means that you end up being sensitive to a good deal more sensitive to changes in those specific directions that you separated over. But that's not true for either of the other two, the Gaussian derivatives or the Gabor wavelets. The main point of this slide is that the derivatives of Gaussians have a lot of intuitive and application kind of benefit because of their relation to the kinds of things we're interested in images, like edges of things or bars and things. But because the results you get from the Gabor wavelets are not all that different from the corresponding results that you get from the derivatives if you have a reason to desire doing it with Gaussian wavelets, you can. The other thing is we're going to see that when we understand the image in scale space, we can start thinking about taking derivatives not only in the x and y, or x and y and z in the case of 3D directions, but also in the sigma directions. We can take derivatives with respect to sigma. What happens as you change scale? Right? And that leads us to something that's called the Laplacian Pyramid, that is a fairly common means of computing, because it turns out that derivatives in sigma are, by the diffusion equation relation, can be shown to be the same as second derivatives in position. Because I remind you, in the diffusion equation, the d by dt has t equals 2t equals sigma squared. So it's t is scale except the square root of scale, if you will, square root of aperture size. And the diffusion equation says derivatives with respect to t are the same as Laplacians with respect to position. And thus, you have first derivatives in sigma corresponding to second derivatives with respect to x and y. Okay? So now we come to the idea of pyramids. And this has to do with the issue of sampling that we've already learned about when we talked about sampling. And with the basic thing we learned in sampling is that the sampling rate should be proportional to the aperture that we're using, right? The delta x should be proportional to sigma. But now we have various sigmas, and so we want to do, the bigger the sigma, the bigger the intersample distance. So people think of it as a pyramid. It's a funny kind of pyramid because its sides are not straight like the ones in Egypt. Okay, but fine. The point is that the full scale of the image that covers this whole range of x, but with a scale that's proportional to the whole range in x, only needs one sample. And here it is. This guy is that. Right? And if you cut your sigma down by some fraction, let's say for this example, by 2, in a moment we'll talk about other possible sampling rates in sigma. But when you do that, then you only need 2 samples across the whole image. Right? Well, 2 in x and 2 in y. This is a one-dimensional picture. Right? It goes out from the board in y as well if you have a 2-dimensional image. And if you are going to halve the scale again, then you need 4 samples in x and in y. And if you want to, that covers the whole image. Okay, so it's the same sort of picture that we saw with the orthogonal wavelets if we're doing explicitly binary sampling. And so then you'd get 8 for one more factor of sigma down, and 16 for one more factor of sigma down, and so on, right? So the point is the sampling needs to be proportional to the sigma at that particular scale. Ideally, though, what you want is that the information at this sampling is specific to that sampling, right? And there are methods that, some that we've seen that go one way and some that go the other way. So some actually try to do the largest scale first and subtract that from the image and leave only information at smaller scales. And then do the next scale down and subtract that out from what's left, leaving a new residue, and then fit that and so on. Just going to let it ring and it'll turn itself off. Or other methods can do the small scale sampling first and then subtract that from the image and then try to go to the next larger scale. So you can work small scale to large scale to small. You don't get the same results depending on which one you get. But there are methods that people do both, and I'm not going to tell you which one to choose, although you'll see why the Laplacian Pyramid has a certain advantage to small scale to large. Okay, so this word pyramid is a big deal in image analysis. If you go to Google and you Google, pyramids in image computing or something like that, you will find lots and lots to read about. These pyramid methods are pretty popular and fairly effective. Okay? So, they can be applied, for example, with the orthogonal wavelet primitive. It builds in that pyramid with explicit binary sampling. But the also quite a popular one is the so-called Laplacian Pyramid, and we're going to talk about that in a minute. Now you can see why I put so much on the board before class, because I'm using class time to put all these dots. Okay, consider this picture where you have, let's say, pixel positions. It can be at any scale, but let's say the original pixel scale. So the basic notion is that that pixel is capturing something with that level of locality. Be careful, by the way. That's normally not the way that's computed. If we want to have a value here, what aperture should we use? A rect function? Ideally, no. What should we use instead? A Gaussian. Well, if we want to use a Gaussian, why not let every position essentially have its own Gaussian? So how would you essentially have a Gaussian weighting at any given position you want, but you're only going to use the center position? Come off with a Gaussian. That's what Gaussian weighting does. How do you convolve with a Gaussian? You go into the frequency domain, you multiply by a Gaussian. Okay, so instead of this idea of aperture with the Gaussian multiplication, which is what we've been talking about so far, from this point of view, we won't do Gaussian multiplication, we'll do Gaussian convolution. Okay, which at the center point, at these points in question, is just the right thing to do. So when I'm drawing these dashed things, they're an indication of the aperture with respect to the center of that square, but not the actual boundary. Okay, but the point here is that if you want to cut down by a factor of 2, you're going to want a Gaussian, if you will, evaluated here, and another one evaluated here. And if this is not the scale of the original image, those x's are also pixel positions. But notice that we can think of the image that way. The dots line up diagonally very nicely as well. And diagonally, the dots are root 2. If they were 1 apart in the x and y direction, they would be root 2 apart in the southwest to northeast diagonal and the northwest to southwest, the northwest to southeast diagonal, right? Which suggests that it's easy to resample in these diagonal directions. And so you will find, as you go to pyramids, some very nice work on this idea that you do horizontal sampling for one scale, and then you move down to the next scale and you sample diagonally. And then the next scale you sample horizontally and vertically again, and then the next scale you sample horizontally and vertically, and that works just great if you're using root 2 as the ratio between successive scales. So the first thing to say is that scale being positive values only are best sampled so equal scales of the equal spacing of log sigma, or equivalently multiplicative spacing. So you don't do sigma and then 2 sigma and then 3 sigma and then 4 sigma. If you're going to have factor 2, you're going to do sigma, 2 sigma, 4 sigma, a sigma. Or if you want to do root 2, you're going to do sigma, root 2 sigma, root 2 squared sigma, which is 2 sigma, 2 root 2 sigma, which is root 2 cubed sigma, and so on. Okay, so we have this multiplicative sampling by some factor alpha, and while you can use other than 2 and root 2, there has been some fairly convincing results that the root 2 ends up giving you some better results than 2. And there's a very significant, well, there is literature about, okay, but what alpha is really right? I mean, just like you want to have decisions based on aliasing effects for the x and y and z directions, or x and y in 2D, you have similar questions that you want to be able to ask about what sampling you ought to have in the sigma direction, beyond the scope of this course to go into that. Okay? Okay, enough about sigma sampling. Whatever sampling we have, I'm going to use 2 as my example. This alpha equals 2, the factor by which we change sigma from sigma to sigma to, well, I have an error in the board and I better fix it. This should be a half, this should be a quarter, and this should be an eighth, and this should be 1 over root 2, and 1 over 2, and 1 over 2 root 2, and so on, right? The successive samples get smaller and smaller relative to some top sampling, or if you're thinking of the sigma 0 as being this, then I was right the first time, right? That is 2 sigma and 4 sigma and 8 sigma and so on without these guys, right? It depends on what you consider sigma 0 to be. If it's the sigma for the top level, because you're going large scale to small, then, well, I'm sorry, yeah, then you have to halve it and quarter it and eighth it, or 1 over alpha squared, 1 over alpha cubed, and so on. But if you think of it as sigma 0 as the sigma of the original image, then you want 2, 4, 8, 16 times that scale. You know, typically people say, oh, I had my original image, it was blurred by some particular sigma associated to the camera, and so I chose my scale for sampling according to that sigma, and that sigma 0, which is the sigma, which is the RMS width of the camera's point spread function, in which case I was right the first time. You want to get successively larger sigmas of 2, 4, 8, whatever, with alpha equals 2 or root 2 squared, root 2 cubed, and so on, with the root 2 rule, alpha. Okay, here's an interesting result. To get a get rid of everything here. At any given scale, if you have no information because you've subtracted it out with residues at smaller scales, for example, what you're trying to do is to take the information at this new scale, having removed it at larger scales. Did I say that backwards? Anyway, whichever. The point is that what you're wanting is g of x and sigma, particularly juicy pen, let me get rid of that so they can see it on the g of x and sigma, which is going to focus on the sigma, this scale, but you want to not use what's at larger scale. So I'm going to subtract G of x and 2 sigma, let's say, on I. So this is, if you will, I of x sigma, and this is I of x 2 sigma. And we want the residue at x sigma to be the difference between what we saw at sigma and what we see at 2 sigma. But because of the linearity of convolution, that's just the difference between the Gaussians at 2 different scales. But an interesting property is this property that I've shown here, that the difference between the Gaussian at 2 scales is approximately equal to the Laplacian of the Gaussian at sigma convolved with I. Well, that's pretty good, right? We can go into the frequency domain, apply a Gaussian at sigma, multiplying, and then multiply by the Gaussian associated with 3 sigma. Not 3 sigma, what is it? Anyway, what you need is to root 3 sigma. So because root 3 squared is going to give you 3, and 1 sigma is going to give you 1, and the result is factor of 4 in the frequency domain, whose square root is 2. And so your point is, by application of yet another sigma on the result of yet a different Gaussian, on top of what you've already computed at 1 sigma, you can get the other one. And then you can subtract those two. And you get essentially the Laplacian. Now you could do the Laplacian directly if you really wanted to. You could actually take derivative operators to get the difference. But it's computationally faster to do it just straight in Gaussian multiplications. And the result is you get what's called the Laplacian Pyramid. So for sigma 0, you can look at the difference between, if sigma 0 is the smallest one, you can subtract out the next larger one, right, and get those differences recorded in your pyramid, and then by inverse Fourier transform. But you already got the g of x 2 sigma computed, and so now you can do g of x 2 sigma minus g of x 4 sigma, and still in the frequency domain, and do the inverse Fourier transform of that result when you multiply it by the image. But you've already multiplied by the image, in fact, and you get the next level up in the pyramid, and so on. Yeah.
So is the residue the Laplacian pyramid?
Say again?
So does the residue give us the Laplacian?
So the residues are essentially the Laplacians, and so this thing is called the Laplacian pyramid. You don't compute it as Laplacian normally. You compute it by these difference of 2 Gaussians. You can play the same sort of pyramid effect with the orthogonal wavelets, but you can play the same sort of game with those as well. Essentially, that's already done by using the kind of a Laplacian, the kind of orthogonal wavelet that has already built in the Laplacian effect, the difference of two scales effect. Okay, so now we have this pyramid. Let's assume we have computed by the Laplacian pyramid approach that I've discussed, but however we compute it, we have this pyramid. And now the idea is that the idea is that information in the image is going to appear optimally at different positions, at different orientations, and at different scales. So that if you have a bar, for example, in the image that let's say it's thin here, then it gets wider here, and then it gets thinner again, and then it gets wider here. Okay, so we have a bar, let's say a dark bar and a light background. That's like that. The point being that at this position, we're going to want an orientation of our second derivative that's like there. But we're going to want a scale that's like that. Whereas here, we may want an orientation, an optimal orientation that's like that, and a different scale. Notice that the idea of using barness, namely a second derivative, is to make the width of the middle lobe of the second derivative of Gaussian match the width of the object. So if we use, you saw, if you use a narrow one, you're going to get very low barness. And if you use a much wider one, you're also going to be less sensitive to this barness. And so you need to optimize over scale, as well as optimizing over direction, as well as finding best positions. Yeah.
So before we fixed our ratio, but now this is letting us vary it depending on the window.
I'm sorry, you need to speak louder so I can hear you.
So before in our assignment, we fixed our ratio, right?
Yeah.
Because we have a constant bar.
Right, because you had a constant bar, and I wanted to make life easier for you there. But now we want to be able to extend to a situation where the bar can change width. Lots and lots of structures in the world have that property, right? They're not equal width as you go along the object. Okay. I mean, my point, for example, is think about an object that looks like this. Well, you may not think of it as a bar, but I'm going to tell you it's good to think about it as a bar. And if you do, it's narrower up here and wider there, and their orientations are different. So, a way of thinking about that for a 2D image is that you have a 3D scale space. Let's leave the orientation out of it for a moment. And what you have here is sigma. What you have here is x, and what you have here is y. And what we're going to be trying to find is a track in scale space that that follows the object, let's say the center of the bar in this example, and is at smaller scales where the bar is narrow, and at larger scales where the bar is wide, and it also varies in position. So now instead of thinking of getting a track in xy, we're talking about getting a track in xy sigma. Right? Which will tell us both the position of the center of the bar, but also the width of the bar. And if we're using second derivative operators in question, then at any given one of these points, the scale in question will need to use a direction which optimizes direction, and that happens to be that eigendirection of the second derivative that you learned about in assignment 5. Right? So now we actually have a position, a scale, and a direction, and that's what we want. So then the general notion there is we're trying to find these tracks in scale space. For a 2D image, you have a 3D scale space, you're trying to find optima in 3 dimensions. Relative maxes. Well, better be careful. Later in the course, we're going to be talking about a notion of what I call a ridge. And a ridge is a subdimensional optimum. Okay, so you go to the Blue Ridge. When I give this lecture in the Netherlands, they may have some difficulty because it's a big flat country. Eastern North Carolina is not a good place to give this lecture either. But okay, we have something like ridges here and big time in the western part of the state. And a ridge is a locus which is maximum as you go across the ridge, maximum in altitude, but not maximum as you go along the ridge. You could be going down or up as you march along the Blue Ridge, but if you're on the Blue Ridge Parkway, it's down that way and it's down that way, right? You're at a relative max in that direction. And it turns out that these derivatives that we're going to need here to find these optima are that kind of subdimensional maximum. We're going to cover that in this course, but at the end of the course. And the reason we're not doing it now, where it would fit logically, is that I want to make sure you get a homework assignment on these geometric transformations like rotation of 3-dimensional images. And if I left that till later, you wouldn't have time to do that assignment. So we'll do ridges after that. We cover the material on geometric transformations. Never mind. If we were trying to find this object, this curve, it'll turn out to be ridge calculations. But the point is, they're calculations in not xy, they're calculations in xy sigma. Okay? And if you wanted to find, let's say, a circular blob, but you don't know what the radius of the circle is, what would you want to do? Well, you want to use the Laplacian pyramid because Laplacians are really good at blob matching. They are themselves circular, Laplacians of Gaussians. But you don't know the scale of the Laplacian you want to apply. Which means you need to find an optimum in the Laplacian pyramid, one particular place in the Laplacian pyramid that's going to be best in sigma, but also best in xy. So it's a proper optimum, not a ridge type optimum in that particular case, a point maximum, not a subdimensional maximum. Okay, one final point here. I've suggested that for bars, the scale should match the scale of the bar. Okay, how wide the bar is essentially, in order to get best match. What about for edges, when we want edginess? We have a choice of using first derivative at some scale or a first derivative in larger scale. Right? What should be the image that this guy is going to be best suited to? Well, frequently edges are at relatively small scale, pretty sharp edges in the image. You know, this pen, if you take a picture of it, really is a boundary between, pretty sharp boundary between the pen and the background. But what happens to that edge when you take a picture of it? It's blurred. Of course, cameras have a point spread function. They're blurred, meaning this sharp change becomes a sloped change in intensity. Instead of the bar appearing like that in intensity, it appears like that in intensity. The background being, so this is the edge. Instead of having this edge, this is intensity, that's x. It's like that. And if it's blurred by amount so that its slope is sort of like that, so if your actual edge of your object looks like that, then you're going to want to use this Gaussian. But if it's been blurred by that, so your actual edge looks like that, then you want to use this guy, huh? So again, you're going to want to find a ridge type optimum in scale space to match the amount of blurring that you have of the particular bar in question. We can also do various singular value decomposition kinds of analysis, because singular value decomposition, which is involves eigenvalues, can be also yields a scale space. Okay, it turns out that the successive basis images that you get from SVD have some number of zero crossings in an interval, and then smaller number, and then yet smaller number, and so on. And so it turns out that the whole business can be played if you happen to do your analysis by our SVD rather than by these other, like the Laplacian Pyramid that I've talked about. Okay, so as I say, we're going to be talking about, okay, so if you have a edge strength image, then you may want to follow a ridge around it. And as I say, we're going to talk about how you find those tracks later in the course. We've already talked about how to compute edgeness and barness, and I'm not going to go through this, and that the optimum barness direction is an eigenvector direction. And that this whole business corresponds to matched filtering. That is to say, you want the kernel to match the shape of the object in question. For example, here versus here, there. Okay? So this is all tied together. Okay. I am going to now stop the lecture, but next lecture we're going to talk about the one factor that we haven't talked about. We've talked about scale of stuff in the image, but what else is in the image besides the actual signal? Noise. And noise is a big deal too. The question is, how's noise going to be understood in scale space? And once I do that, I'm going to disabuse you of what's commonly said in the literature, that taking first derivatives is harmful with respect to noise. Okay, you will see you will see next lecture that that's not only a wrong statement, it's a foolish statement. Okay, we'll talk about that later.